Hey y'all, here we are. It is time for the last video of the class. This is it, the final day. It's been great. It's been quite a journey. Let's do it. What we're looking at today is first a little bit about the three-dimensional Fourier transform, because we live in 3 dimensions or four. And in order to do that, basically what we do is really just take our position and our frequency and we just turn them into vectors instead of being scalars. So position vector, no big deal. You're used to that. Left, right, up, down, forward, backward. What does it mean to have a frequency be a vector? Because normally when we're thinking about frequencies, we're like, we just think about them as scalars. It's just a rate of oscillation. Well, a frequency vector is when you have a wave in 3 dimensions, it can have different wavelengths in different directions. And going back to the scalar definition of k as 2 pi over the wavelength, then you can say, okay, well, if I have different wavelengths in different directions, then I can have different values for k in different directions. And those are the components of the wave vector, are k1, k2, k3 in your x and y and z directions to account for the fact that the wave can have different wavelengths in different directions. Okay. And once you've got that, then you can start to do crystallography. You can start to talk about solids. You can say, I have a lattice. There are atoms at different positions in this lattice, different distances, different angles with respect to each other. And as long as it's a periodic structure, you can do all this Fourier analysis. You can look at its frequencies and say, what are the frequencies of the waves that live on this lattice? What are the waves whose frequencies are compatible with the spatial frequencies in different dimensions, in different directions in this 3 dimensional structure? This is really kind of the foundation of crystallography. All the business that you learn about structures and lattices and all of that, a lot of it actually does come down to Fourier analysis at the end of the day. So we need to get to an n-dimensional system. How are we going to get the math there? Well, here's our regular one-dimensional definition of the Fourier transform, transforming from little f of x to big F of k. Great. When we have 3 dimensions, we don't actually have to change very much at all. We have to turn our positions into vectors. We do pick up some extra factors of square root of 2 pi out front. That's just the normalization. You get one factor for each dimension that you have. So if you're in 3 dimensions, it'll be 2 pi to the 3 halves. And you'll have a volume element instead of a length element for your integral, because this will now be a multiple integral over all your different position values. And then in the argument of the exponential, you do have a dot product. So this is going to be the wave vector k dot the position vector x. So that'll be k1 x1 plus k2 x2 plus k3 x3 for the components of those vectors up inside the exponential. And that's it. That's actually all you have to do. It's it's not always easy, but there's not any extra concepts that you have to bring in. It's the same framework as what we've already been doing. We're going to revisit the Dirac delta function. This has come up several times recently. It's a really useful little tool to have. So what's going on here? The transformation of a delta function. I haven't said yet why we're doing this. Just come along for the ride with me. Well, the thing inside the integral is 0 everywhere except for where the delta function is, where it has its spike. And that means that when we integrate, when we actually evaluate this integral, you get 0, 0, 0, 0, 0, 0, something, 0, 0, 0, 0, 0. And what that something is it is the value of the integrand at that one position. So this is the x1 in the exponential here, is that's the location where the delta function is positioned. So The effect of the delta function in the integral is to grab one single value and just pull that out. That's basically what it does when you integrate it, because all the other values get zeroed out because the spike is infinitely narrow. 0, 0, 0, 0, something, 0, 0. So we get just the something when we integrate over all values of x. Cool, great. What do we do with this? What we do is we start to build a lattice. Hypothetically, just, I don't know, stick with me here. Suppose we had a lattice and I was like, yeah, I want to take its Fourier transform because I'm feeling pretty good about myself, about all this crazy and complex analysis stuff that we've done. And yeah, I think I'm just going to do this and see what happens. Well, let's do it and see what happens. One way to describe a lattice is as a collection of delta functions. Each atom is a point in the lattice. I'm at this corner of my cube, or I'm in this uh, center of the cube, or I'm in some position in a hexagon, or your orthorhombic whatever business, tetragonal, all those structures, things. Uh, each of those points inside your unit cell where there is an atom, you can describe the function as a delta function because the atom is at that one point and it is not anywhere else. So our function that says, hey, where do I have atom in my lattice, just starts to look like this. It's just a sum of delta functions where the x1 and the x2 and the x3 are the positions of the atoms. Now, for actually doing a calculation to derive a result, I am going to do this in one dimension. The story doesn't change in 3 dimensions. It's just 3 times as much stuff to write down, and I don't think it helps with clarity. So we're going to do 1 dimension, but the same result does extend in the same way to 3 dimensions. Again, you just have to write 3 times as much stuff. So we're going to have a 1-dimensional lattice. It has a lattice parameter A. And so there it is. This is a bunch of atoms that are all a distance a apart from each other. And this means that we can write the function of the lattice, the function that gives the positions of all of the atoms, as a sum of delta functions. And this is actually just going to be an infinite lattice. So it's going to be periodic forever and forever and ever, all the way off into infinity. And that's why we're summing over infinities here. And at each uh, integer value, so n is integers here, every time you add another integer a, you just go 1 atomic site to the right. Add a, add a, add a. So that's why we have all these delta functions at NA. This is the spacing of each of those deltas. Cool. So we've built a lattice, we've written it as a mathematical function. That means that we can do calculations on it, like Fourier transforms. Now, I did mention this in a previous video, but just to reiterate, the Fourier transform is a linear operator. So if you feed in a sum of different functions into a Fourier transform, you get the sum of the transforms of the individual functions. So instead of writing this giant ass integral every time, I'm just going to start writing curly f. So Fourier transform of a sum is the sum of the individual transforms. What this means is that we are now taking the Fourier transform of the sum of a whole bunch, infinitely many, delta functions. That means that the result is the sum of the individual Fourier transforms of all of those individual delta functions. This is the power of linear operators. So now what? Well, now we have to get the Fourier transform of a delta function, but I already showed you how to do that. So what else do we need to know in order to work out this calculation? Well, to figure out the scaling of our axes, this is going to be a U substitution problem. So when you're making a linear operator, you can add terms together, but you can also multiply terms by scalars. When you multiply a function by a scalar coefficient and then take its Fourier transform, the answer that comes out is 1 over the scalar. That's what's happening here. And then you get k over that scalar in your result. And why is it divided by a instead of times a? That's where you do the u substitution business to show where that comes from. Where when you have u equals x times a, and then du is a dx, and then you substitute in du over a equals dx, that's the over a that's happening. I probably should have written that out, but words. Sorry. Okay. The last thing we need to know, this is actually a problem on the homework, by the way. This week's homework is show that this is true. So, bam, here's the answer, by the way. You still have to do the process of like working it out, but this is how the result ends up being. So if you take a function and you translate it by an amount b to the left or right, you still get the same answer, but it's now multiplied by a phase factor e to the I, however far it's translated. And there's actually a way that you can think about this in terms of wave motion to sort of explain physically why a phase is a reasonable result to get from a translation. But I probably shouldn't make this video even longer, so I'll just say, hey, this is on the homework. All right. We now have all the ingredients. It's a linear operator. We know how to deal with translations, and we know how to deal with scaling. If we can translate and we can scale and we can add and multiply things, we're good to go because we know how to deal with all the individual components now. So here is our Fourier transform written out. Yes, this is an infinite integral over an infinite sum of a function that is infinitely tall. It's infinities everywhere, just infinity and beyond. It's fantastic. So infinite. Okay. But at the end of all of this, because the integral of a delta function is easy, the answer that comes out is that the x in the integrand just gets replaced with NA because that's the only location where the delta function is non-zero. Cool. Now, there is still the matter of this little infinite sum here. I hit all the infinities to make it less scary, but yeah, this sigma right here, that is the sum of all the infinite integers that there are. So how are we going to evaluate this thing? Because adding together an infinite number of complex exponentials doesn't necessarily seem obvious. Well, what you have to do is you have to go all the way back to your algebra class. Remember how we completed the square recently? We're still digging back into our high school algebra. In the geometric series, maybe it's pre-calc, I don't know anymore. You can rewrite this by the properties of exponentials. We had e to the negative ikna. Well, that's e to the negative ika raised to the nth power, right? Since an exponential raised to a power, you multiply the power by the exponent. So we can rewrite this as an infinite sum of a term raised to a power. You're like, why is this better? It's better because there is a formula. When you have a number between 0 and 1 and you raise it to a power and you sum over the series of all of those increasingly small terms, because the power gets bigger and bigger, r is a number between 0 and 1, the series will converge because each of those greater powers is closer to 0. This is a solved problem. It's in your algebra book. So this is the result. The value of the sum, the infinite sum, the value, oh my goodness, words are so hard. The value of the sum of a geometric series is given by this fraction. And r is e to the negative ika. And that is a number between 0 and 1 in magnitude. It might be a complex value, but it lives somewhere in the unit circle in the complex plane. So we're cool. So you plug in your result. Great. Now what? This is starting to become so much better because instead of an infinite sum, now we just have a fraction. This is getting better. Now we gotta be clever to simplify this further. You can write e to the ix in terms of sine and cosine, which means you can write sine and cosine in terms of e to the ix. So here's our formula for sine of x. And if you solve for, I know this looks worse. Yes, it is worse, but it will get better. But if you put in these expressions, the over 2i's all cancel out because they're on the top and bottom. I already took care of that. What we're left with here is a common factor. E to the ikna over 2, e to the ika over 2, ika over 2, ika over 2, ika over 2. So we're going to take that common factor and just pull it out of everything. And what that leaves you with is this factor out front times two different signs. There's a sign on top and a sign on bottom. Hey, look at this. That's your sine function, right? E to the negative stuff minus e to the positive stuff. E to the negative stuff minus e to the positive stuff. It's right there. It's right there. So these are actually sine functions. These aren't, you have that constant, you have that complex coefficient, but the rest of it is actually just sines. That's crazy. This is great. We're getting somewhere. We're reducing the amount of bullshit that's on the page, and that is called progress, my friends. All right. I actually forgot that was the title of the slide. That's really funny. Oh, wow. All right. I hope you're enjoying the ride. So collecting all of this business, putting it back, putting the result back into our Fourier transform result, we have this complex exponential factor out front. We have sine of kna over 2, and then sine of ka over 2. And this is a function that you encounter in your first semester of calculus. This function, sine of nx over sine of x. Like when you're learning L'Hopital's rule and you have to figure out, hey, what's the limit of this thing as x approaches 0? Because like it's 0 on top, but it's 0 on bottom. What happens to 0 over 0? Oh my God, math. Like that stuff that happened in calculus. The properties of this thing, this sine of nx over sine x, the properties, again, this is a solved problem. There's nothing new here. You might have forgotten the answer. That's okay. I'll remind you the answer. But this is math that you know how to deal with. This is Calc 1, Calc 2. This is, oh, by the way, you can do this in terms of Taylor series. Did I say that out loud? Okay, so as your number of terms increases in the sum, then for the most part, this ratio is going to be 0, except at, again, the places where the sine function goes to 0. And the sine function goes to 0 where the argument is an integer multiple of 2 pi. So 0, sure, but then 2 pi, 4 pi, 6 pi, so on. And that's what I'm showing graphically here. This is the value of that, that quotient of these two sine functions. Basically nothing, something. Basically nothing, something. And the different squiggles that are being drawn here is showing the result for, again, just different numbers of terms in the series. Okay, great. So this is something that can be evaluated. And what's important is it's it's non-zero only in very specific values of Ka. That's important because when you look at this result, what you get is a coefficient, all this business, all this business, all this business. That's just a number. It's just a number. It's a complex number, but it's just a coefficient. The shape of the function is given by this ratio of the two signs, which is 0, 0, 0, something, 0, 0, 0, something, 0, 0, 0, something with a fixed period. And that is also a lattice. There's something right here. And then 2 pi later, there's something here. And then 2 pi later, there's something here. And then 2 pi later, there's something here. The Fourier transform of a periodic lattice is another periodic lattice. It lives in a different space. It's in frequency space. And the distance between these things, k equals 2 pi n over a divided by. So you get this series of spikes. We transformed our delta function array into a different delta function array, and 2 pi over a is the lattice constant of this new transformed lattice. It's the reciprocal of the original lattice constant, and that's why this is called the reciprocal lattice. So there's your conclusion. This is what the reciprocal lattice is. It's the Fourier transform of the spatial lattice. It is the lattice whose spacings correspond to the frequencies of waves that live on the original lattice of atoms. It's wild. And that's the thing. That's our semester. Hooray, you made it. We're here at the end. I'm so proud of us. We did the thing. So that's pretty much all I got to say, actually. Like and subscribe and whatever else people do on the internet these days. Also, in all seriousness, uh, do your course evaluations. It is meaningful. I do read all of them. This is only the second time I've taught this class. I am definitely going to make changes next year. Help me make better informed changes by telling me your experience. What was good? What was bad? What sucked? What was awesome? I am absolutely wanting your feedback on that. All right, I guess it's time to sign out. So I'll see you. Oh, yeah, JK, why it matters. There are many applications for this, but this little picture on the right here, this black and white speckles of things, this is the original X-ray diffraction photo. This is from Lau's, I want to say 1912 paper, where, yeah, he sent X-rays through a copper sulfate crystal and so he took a copper sulfate crystal, shined X-rays through it, and then those X-rays hit photographic film, and so they exposed the film, but the X-rays only exposed the film in the points where there was constructive interference between the X-rays bouncing through the crystal. And those are all of these dots that you see in the photo. These are the locations where the X-rays added together instead of canceling each other out in order to expose the film. And that's caused by the wave numbers of the X-rays interacting with the lattice, and in directions where you have these complementary frequencies, they're going to add together. You can actually solve this problem entirely in terms of the reciprocal lattice and say, hey, where do the symmetries of my reciprocal lattice line up with the frequencies of the waves that are coming in? And that's where you get constructive interference in your diffraction pattern. So working backward, if you have an unknown material, you're like, what is the crystal structure of this thing? That's important to know, but I don't know what it is because it's a new material. Well, you shine X-rays through it. X-ray wavelengths are typically about the same size as the spacings between atoms in a lot of solids, so they work great for diffraction measurements. And as you send in X-rays, then they are going to bounce off of atoms in the lattice, and that's what's shown in this picture on the left. But not all of those X-rays go to the same place. They're all spread throughout the crystal, and so they'll bounce off of different atoms and travel different distances. But the distances where the waves travel and whole extra number of wavelengths, that's what's being shown right here. One extra wavelength traveled, you'll get constructive interference. And you can understand this again in terms of what are the wave vectors of the X-rays and what are the wave vectors of the reciprocal lattice and where do those line up with each other. So this is arguably the number one method of saying where are atoms in materials? And it all starts from there. So there we go. That's why it matters. And now with that, I'm actually going to sign out. I hope you have enjoyed this class and learned some things. And I hopefully will see you again in the next episode of whatever this crazy thing is that we're all doing together. Later. This was a really long math class. We studied a semester or more. I thought we'd get bored, but that doesn't happen because the math is exciting. All the answers, things that we learned, they told us a lot about math. And though we were scared, we thought it'd be hard, we learned about so much and more. We thought we'd get there, and now at last it's the end.